Okay, I am going to go through the notes real quick. The first thing that we need to do is add an x and a y axis. So you just want to put them somewhere towards the middle. Sorry if the adjusting as I draw gets a little annoying. I'm probably going to move this just a little bit to the right so I have some more space to write over here. All right, we are talking about quadratic functions. So quadratic functions, first we are going to define as functions whose highest exponent is 2, or they have a degree of 2. So this would be when we are looking at the equation, we would have a degree of 2. Remember, degree means highest exponent. If we're defining when we're looking at the graph of a quadratic function forms a parabola. Now, a parabola is a new shape, but it is this U-shaped graph. So it's going to look like this or like this. It keeps going up and out or down and out. But a parabola is a U-shaped graph. You will see that word and hear that word parabola here as well as in Algebra 2. And then you will look at quadratics again if you continue past Algebra 2 in college algebra or trig, different things like that. Thirdly, or our third representation of a function we know is a table. If we think back to linear functions, we know these same things about linear functions, and we talked about this in class, but the equation of a linear function has a highest degree of 1. A graph forms a line, meaning it must be straight, and a table has a constant rate of change. The tables for a quadratic function do not have constant rate of change, but they do have a pattern. The graphs and the tables are symmetrical about a particular point or about the axis of symmetry, which we will define here in a minute. So they are centered around also a point called the vertex. Again, we'll define that here in a second. But let's go ahead and look at one particular equation. I want to look at the equation y equals x squared minus 6x plus 5. We're going to look at this as our example for all of quadratic functions, so we'll use it on the front and on the back of our notes today. But we want to keep that in mind. I'm actually going to change it to pink because I'm going to use pink to graph my function. I'm going to try to color code these as I go so you can keep up with those key features and where they are important. Now, in order to plot points, this isn't a line, so I can't say, hey, the y-intercept is, the slope is. There is no slope because it is not straight. It does not have a constant rate of change. So instead, we need to create a table. So if you come down here to the bottom, you can use the white space at the bottom of your page or the bottom corner of this graph, either way. But we have our x and our y values. We want to pick both points that are positive and negative so it shows up on both sides of the graphs. If we only pick positives, we'll only be able to see our graph on this side right here. But we want positive x values and negative x values so we can see the full picture. So I'm going to start off by using -3. What you're going to do this, I'm going to be jotting and erasing, but I would use my equation, and where the x is, I'm going to plug in -3. If you throw this in your calculator, it'll simplify it for you, or you can work it out by hand. -3 squared is 9. -6 times -3 is positive 18. Plus 5, and we then simplify that by combining like terms, we get 32. We're going to do that again. Oops, wrong tool. Until we fill out this whole table. So I do it again for -2, and then -1, and then 0, until I've managed to fill out our whole table. I will work through probably 2 more of these just so you can get in the habit of seeing it set up, but I'm not going to work through all of them on the video. I'm just going to jot out what the points will be. So when we do -2, same thing, -2 squared minus 6 times -2 plus 5. I get 4 plus 12 plus 5. I have 21. I am going to keep going. I'll skip a couple so we know when we plug in -1, we get 12. When we plug in 0, let's talk about 0. 0 squared minus 6 times 0 plus 5. 0 squared is 0. -6 times 0 is 0 plus 5. So we notice we get 5. Could we have picked this up from the equation? Someone in class pointed out that we could have, that it is that last number, and that is a key thing we are going to talk about in just a minute. So you'll notice there's a lot of pieces that fit together, and they're going to reiterate, and they all connect. That's the big idea. We want to draw the full picture of this function. If I plug in 1, I get 0. If I plug in 2, I get -3. If I plug in 3, I get -4. If I plug in 4, I get -3. We'll come back to that. If I plug in 5, we get 0. If I plug in 6, we get 5. Now, can we think about what would I get if I plugged in 7? Let's look at the pattern and talk about what it means to be symmetrical. So we've already defined that it is symmetrical. It's the same on either side. You can cut it in half and it is a mirror image. So if we look at this table, it is symmetrical because notice these points, these values, not the full points, they start to repeat. We have 2 outputs that are 0. We have 2 outputs that are 5. We have 2 outputs that would be 12. And this is going to keep going. We would see the symmetry along the full table and as well in a second the full graph. But we've got that symmetry started so we can see that these are symmetrical, and we'll notice that, hey, in that symmetry there is one point right here. This is the middle. It starts being symmetrical on either side of this. So we're going to come back to this idea that this is the middle and figure out what that tells us, or what this value being at the middle tells us. Now that we have our points, I'm going to zoom out. We want to go ahead and plot them on the graph. So I'm going to take each one of these points and plot it out on the graph. 1, 2, 3, 4, 5. So I have 0, 5. I have 1, 0. I have 2, -3. 3, -4. 4, -3. 5, 0. 6, 5. 1, 2. -1, 12. Now, if I go to plot -2, 21, 13, 14, 15, 16, 17, 18, 19. I only get to 19. So we know that this graph is going to continue up past what we can see on our graph. So we would draw arrows at the end of this to show that, hey, it does keep going up. But I can go ahead and add this point right here. And I'm going to connect my dots. You need to be very careful when you connect your dots. I'm going to use my quick tool here to show that it's going to keep going up and out. But we want to make sure that we can see, hey, this is, oops, gonna keep going. So I'm gonna extend it a little bit to show it does keep going. Now that we've got our points plotted, let's start talking about the key features that we see on this graph. So on this graph, first thing, it's a point we've already talked about in previous units. We looked at it when we had exponential functions, we looked at it when we had linear functions, and we've already mentioned it once here. We know that the y-intercept is 5. I can see it in the table. I know that this point right here, 0, 5, is the y-intercept because the x value is equal to 0. So if I wanted to go back and add myself some notes on y-intercepts, and just kind of have a little refresher, a y-intercept is where your graph crosses the y-axis. At this point, x is going to be 0. So every y-intercept has an ordered pair that is 0, comma, number. In this case, 0, comma, 5 is our y-intercept. Now, we also can see what we call the x-intercepts. I'm going to move that label. Try to make everything fit. Okay. We also see what we have as the x-intercepts. Blue is going to be my color for x-intercepts. So we notice here, these are the 2 points where they cross, or it crosses the x-axis. All right, where the graph now, opposed to previous functions that we've looked at, such as linear and exponential, you can have more than one x-intercept. Here, we will either have 1, 2, or no x-intercepts, depending on the individual function that we're looking at. But quadratics can have 1, 2, or no. This is where y is equal to 0, meaning every ordered pair for an x-intercept is going to be number, comma, 0. In our case here, we have the point 5, 0 and 1, 0. We can also go back and see these in our table as we have 1, 0 and 5, 0, and we know that these values are x-intercepts. I don't like it written like that. I'm just going to put it above it. All right, the next key feature we want to talk about is new for quadratics. It is not an element that exists in exponential or linear, but we want to look at this point right here. It's the lowest point of our graph, and this point we call the vertex. The vertex is simply either the lowest or highest point. It can be referred to as a maximum or a minimum. But the big idea here is your vertex is your turning point. A vertex is where the graph turns around. And this is the first time we've had a function that turns around. A exponential function is a curve, but this one literally turns around. At first, we notice if from left to right, if we trace it, it's going down. Once it gets here, it is now going up. So we can describe that as decreasing and then increasing. It is a turning point. This will either be the highest point of a parabola or the lowest point. Now, a parabola will not have both a highest and a lowest. It will do one or the other. When it has a highest point, we call this the max. When it has a lowest, we call this the min, or minimum and maximum. Here, this very obviously is a minimum. From our table, that's going to be that middle. This is my vertex. It is the point at which the graph turned around. So we know that 3, -4 is important because it is my vertex. All right, last thing, we're going to go back to that idea of symmetry. And we know it is symmetrical about that vertex or that middle. So there exists what we call a axis of symmetry, or a line about which it is symmetrical. It's a line that cuts right down through the middle of our graph. It is invisible. It's not really there, which is why I represented it using a dotted line. But the axis of symmetry is also a new component for us for this unit. And I'm going to come put all my information for axis of symmetry right up here. So, an axis of symmetry. First thing, let's define it. It is an invisible line down the middle about which the quadratic is symmetric. We will notice that the points of this line are going to be equidistant, or the points of this graph are going to be equidistant from this line. Here, these are each 4 units away from our line. Here, these are each 3 units away from our line, our middle. If I went to one of these, we'll notice that it's 3 3/4-ish, 3 3/4-ish. I don't have that exact decimal here. We notice they're each 2 units away. They're each 1 unit away. So we can see that symmetry because it goes down the middle. The other thing is we need to know that the axis of symmetry is written as an equation. And that equation will always be y equals a number. Now, this number is going to be the x value of your vertex. Our vertex is 3, -4. So here, that would be x equals 3. It's the x value of the vertex because it is the vertical line or the undefined line through that point. When we talk about finding it from an equation, when we don't have a graph or we don't already know our vertex, we can use a little formula, y equals -b over 2a. And this would be the equation or mini formula to find just the axis of symmetry. Now, in our geometry unit that we just finished, we also referred to an axis of symmetry as a line of reflection. So that is something to keep in mind. That is an important piece of information. So that pretty much goes through everything that we did on the first day. We then flipped over to the back side of our notes and we practiced a little bit. We looked at these examples and said, hey, where are these x-intercepts? Where do they cross? Well, that would be -3, 0, and -1, 0. We want to look at the y-intercept, so we find where it crosses on the y-axis. That point is going to be 0, -3, because this is where x equals 0, whereas the x-intercepts are where y equals 0. Our vertex is going to be the turning point, so if I come up here to that highest point, our vertex is a maximum this time because it's the highest, and we see that it is the ordered pair 2, -1. If our vertex is 2, -1, whatever the x value is the axis of symmetry. So I could draw that invisible line down the center of my graph, and I would know that, hey, this is a axis of symmetry. It's that invisible line about which it is symmetrical. Today in class, we tried to focus on the 3 different forms of the equation. That's going to be the bottom part. I will make a second video for that.